Using the solubility of a compound to calculate KSP. The key to this is that solubility is in grams per liter and molar solubility is in moles per liter. So if you can convert solubility into molar solubility, you have the concentration in terms of moles per liter of the ions from your sparingly soluble compound at equilibrium. So the first thing you have to do is calculate the molar mass of your compound. So in this case, my molar mass of my silver chromate, I guess I should probably say silver 1 chromate, is going to be 2 times silver, so that's 107.87. Obviously, use your periodic table to use the appropriate amount of sig figs, and then chromium is 52, and then each oxygen is 16. Add those all together and I'll get a molar mass of about 331.74 grams per mole. That's good enough for me. Okay, so then I can use that as a conversion factor. So I would rewrite that. For every 1 mole of silver 1 chromate, that weighs exactly 331.74 grams, because then I can take my molar solubility of 0.022 grams per liter and then use this as a conversion factor to get to moles per liter. So 331.74 grams weighs is the weight of 1 mole of my silver 1 chromate. Okay, so let me just make that look prettier a second. So we can see that grams is going to cancel, giving me molar solubility in moles per liter, and that shakes out to be 0.0000006632 moles per liter. That will do for sig figs, because see we're only going to need 2 sig figs at the end, based on the 0.022 of the solubility. So we should write a KSP expression to know what we have to substitute in. And honestly, I think it is very advisable to actually write an expression for the dissolution of your ionic compound, because you need to make sure you catch the stoichiometry. Every 1 mole of silver 1 chromate that dissolves is going to yield 2 moles of silver 1 cations and 1 mole of the chromate anion. So do make sure that you actually complete that step, because you need to know the stoichiometry. So then I can write my KSP expression. So my KSP expression is going to be the concentration of silver plus at equilibrium raised to the power of 2 times my concentration of the chromate ion at equilibrium as is. So I can just substitute this in, okay? But let's be a little bit cautious with the stoichiometry, okay? So this is going to be whatever X would be in my ice table, right? So if I'd done an ice table where I was solving for the concentration of silver and chromate, I just realized I missed a 2 minus off that. Very naughty of me, 2 minus. I would pick my chromate to be my plus X. So we're going to start with 0 of each of these, right? And then, so initial, and then my change is going to be plus X for my chromate ion, okay, because for every 1 mole of silver chromate that is dissolved, I'm going to be yielding 1 mole of the chromate anion, but for every 1 mole of chromate anion, there'll be 2 moles of silver plus 1, because look at the stoichiometry, there's 2 silver ions per mole of silver chromate, okay? So when we get to our equilibrium row, to substitute into our KSP expression, that's going to be 2x and x. So our concentration at equilibrium of the silver is not 0.00006632, it's 0.006632 times 2. So just be really careful with stoichiometry. I've warned you once, okay? So 2 times 0.00006632, and then we'll square that, okay? And then times that by the concentration of the chromate ion at equilibrium, which is 0.00006632. So my KSP is going to come out to be 1.16679 times 10 to the power of minus 12. Tiny. We're asked for 2 significant digits. So let's look at the next one after after the 1.1, that is over 5, so that will round to 1.2 times 10 to the minus 12 to 2 sig figs, okay? So you've got to watch the stoichiometry in two places, okay? First of all, in writing your KSP expression to begin with, and then second of all, notice for your concentrations at equilibrium, what that will actually do to your change row and your ice table. You don't have to go ahead like I did and write the whole thing out, but just remember that that means that your equilibrium concentrations may not just be X and X. So you've got to actually know if it's 2X or whatever it may be. Okay, well, hopefully that helps you solve those kind of problems.